Hello, good morning everyone. Today I will give a presentation about multi-party, distributed, and collaborative learning. This is the outline of my presentation. We are familiar with AI or machine learning. AI or machine learning has been widely used in all aspects of our lives. Okay, let's look at the first use case of AI. As we know, intelligent medical is more and more popular in our daily life. Intelligent medical powered by AI and big data promotes the health development of human beings. The performance of AI is decided by high-quality models and large amount of training data. However, the medical data owned by many hospitals or medical institutions. For example, in China, there are more than 30,000 hospitals and 1 million medical institutions. And medical data owned by the top 20 electronic medical record manufacturers are less than 20% of the market. So the current situation is that data are powdered in many medical institutions. Here is another classic use case of AI. AI can be used in cyberspace situation awareness with the ability of detection and prediction, such as detect the security event, network threat, network attack. In this use case, it requires massive network records to train a high-performance security model. However, for example, in China, there are thousands of cybersecurity enterprises. These institutions are unwilling to open source their security records due to the intellectual property considerations. So, the situation is that security records are fragmented in many situations. Okay, the situation is that data are distributed in large amount of independent parties. For example, enterprises, schools, research and medical institutions. We call this phenomenon as data island. For a single party, data is not enough for training a high-performance model. Therefore, multiple independent parties should collaborate to train a high-performance model. Therefore, multi-party collaborative learning comes into our lives. It can use the data from distributed data islands to train a high-quality model. For each domain, inter-party has different characteristics with inter-party. For example, in inter-party, there may be high bandwidth and low delay, homogeneous resources, safe, reliable, and trusted. But in the inter-party, there may be low bandwidth and high delay, heterogeneous resources, unsafe, unstable, and untrusted. So the data sharing is the first problem needed to be solved in multi-party collaborative learning. Through data encryption and distributed file storage, sharing data with each other while ensuring that data is not stolen nor tampered with. However, there are some limitations for the data sharing in multi-party collaborative learning. For example, the heavy transfer load and data privacy consideration. Independent parties should not share data without users' permission. The second solution for multi-party collaborative learning is federated learning. In federated learning, parties share knowledges rather than raw data between central party and participating parties to train a shared model collaboratively. Federated learning avoids exposing the sensitive data to insecure network and untrusted third parties, thus protect the data privacy of users. However, there are also some limitations for federated learning. For example, too many collections in one heavy communication load in the central party wasted computing resources. Two key ideas are included in this hierarchy framework for collaborative learning: knowledge sharing and hierarchical architectures. In this framework, there are three kinds of loads in this framework: worker, server, and globe server. Each party aggregates the local training results and sends the local model to global server to get the global model. It can reduce the communication load of the central party dramatically, make full use of both computation and communication resources. It can flexibly select intra-party synchronization algorithm, for example, parameter server or reduce. There are also many challenges. For the challenges on efficiency, since there are large amounts of data need to be transferred during the training process, the communication becomes a bottleneck of training in the central party. The other challenge is strong heterogeneity in both communication and computation. Since different participants have different types of devices and communication bandwidths. There are two main problems in strong heterogeneity. The first one, straggler problem in sync model. The powerful devices are blocked to wait. The strangling devices. The second one, it may delay the gradient in async model. It may be used too updated gradients to update the latest model. This may damage the model accuracy and convergence. For the challenge on security, someone may leak and tamper the training model. The server may be honest but curious. Central party is curious about the data from specified parties. It may inspect their model gradients to learn the data. The next important challenge is trustworthy. There may be some untrusted participating parties in the training process. They may push invalidated gradients into servers and thus slow down the model training, destroy model performance, or leave backdoors in models. The fairness is also an important challenge. For the participating parties, unfairness may cause the following problems. The first one, discourage parties to contribute high-quality data and strong computing power. The second one, more performance to deceive with invalid data. The third one, inefficiency and poor model performance. Thus, we have to estimate the contributions of participating parties fairly based on the data size, data quality, contributing resources of each party. For the inefficient architecture of the existing federated learning, we proposed a new hierarchical parameter server framework we called heaps. For the high communication delay, we proposed an efficient transmission protocol called DGT, which transfers the important data in reliable channel with high priority and transfers the unimportant data in unreliable channel with low priority. It can reduce the communication delay by up to 46% and accelerate job completion by up to 1.4 times. For the diagonal problem, we proposed a new synchronization protocol called eSync, which coordinates the number of local training iterations. It can achieve more than 27 times acceleration complete compared with the existing method. For the Medicers model attack, we proposed a soft decentralized selective DGT, called SGD approach, which ignores the low accuracy model updates. Our method is compared for FedAVG, is secure is in secure user networks. It is robust to various model attacks in untrusted user networks. The last one, for the challenge on lack of fairness and incentives, we designed a blockchain over multi-party collaborative learning architecture. It is a secure, robust, and fair multi-party collaborative learning framework with incentives. Okay, in our we have proposed multi-party collaborative learning use hierarchical architectures to isolate intra-party and inter-party. Therefore, it is a natural choice for both network intelligence and data privacy protection. We have developed a hierarchical parameter server software prototype, heaps, for multi-party collaborative learning, and are making some interesting work on the efficiency, safety, trustworthy, and fairness in this field. We have built a combined framework binding the blockchain with AI to make the network intelligence safe and trustable. That's all for my presentation. Thanks for your attention.